Bandwidth for changelog is provided by Fastly. Learn more at fastly.com. Error monitoring is provided by Rollbar. Check them out at rollbar.com. And we're hosted on Linode servers. Head to linode.com/changelog.
I'm Damian Gryski, and it is go time.
It's Go Time, a weekly podcast where we discuss interesting topics around the Go programming language, the community, and everything in between. If you currently write Go or aspire to, this is the show for you. Welcome back, everybody, to another episode of Go Time. Today's episode is number 66. On the show today, we have myself, Eric St. Martin. We have Carlicia Pinto here.
Hi, everybody.
And Brian Kettleson.
Hello.
And our special guest today, who I'm really excited about, is Damian Gryski. And most of you may know him because he's always talking about white papers that I know personally I wish I understood enough to read. But you wanted to, I guess, before we jump into kind of like performance and fuzzing and stuff, do you want to give people a little background on who you are for anybody who may not be familiar with you already?
Okay, well, so my name is Damian. I've been using Go since before 1.0. I remember things like os.error. I tweet a lot about Go. I'm the moderator of the Go subreddit. I post a lot of stuff there too. I like, sort of computer science researchy things. So I have a lot of repositories of papers and stuff that I've implemented. I used to live in Amsterdam working for booking.com, but now I am in Vancouver working for Fastly. So that's me in 30 seconds.
Do we know anybody else that works at Fastly?
I think so.
No.
I can't. I'm trying to think of somebody, but I can't think of anybody. Feels like I should know somebody that works at Fastly.
So before we kicked off the show, we were kind of having our little pre-chat there, and you talked about how you kind of did like busking and magic and stuff beforehand. So I actually find it really interesting because you decided later to learn computer science, and then you went like all the way over. You're like, I'm going to deep dive and read papers and implement them and write papers. Like that's awesome.
Growing up, I actually just had this discussion with my daughter and my wife's parents. We were all talking about what did you want to be when you grow up, and I realized that even though there was a brief period where I was hanging out with jugglers and magicians and thinking maybe this is a cool thing that I could do because I was 12. I started programming very early, and I have a book in math stuff from when I was in grade 5, 6, really being into math and computers and programming and doing all that. So it's not that I totally switched. It was just like, oh, wait a minute, actually this is just a better career path for me.
So both hobbies, you just kind of switched which one should be your career.
Yeah.
That's awesome. So one of the things that you talk about a lot recently is performance. So let's chat a little bit about performance and when's a good time for focusing on performance. With something that's already so fast as Go. When and why does it matter to start looking at performance? All that good stuff.
So I guess I'll quickly talk about this perf book that I'm writing. So I tend to mostly hang out in the performance channel on the Gophers Slack. And, one of the things I was like, we have sort of, so much, knowledge about, how to optimize Go and, ways to build things and ways to work around issues in the, runtime and, getting better performance out of the compiler and all that. I said, we should really gather all these blog posts and actually turn this into a resource to take it sort of out of, 20 people's heads and onto something that would be easier to share. And so I sort of, got, a bunch of resources and, started writing up a little bit of, things that I, my personal thoughts about optimization and performance work. And, every now and then I would sort of add a little bit to it. And then I think, around the beginning of the year, I was going through my repositories and I noticed, oh yeah, there's this perf book here. It's like, oh, but it's kind of stalled a little bit. And so I made some dumb tweet. It's like, clearly the reason that, this hasn't taken off is because, it's not called, like awesome Golang performance and, is now on the front page of Hacker News. And that tweet actually got a whole bunch of retweets. And, I got, like 200 stars in like 24 hours. And like, wow, okay. So clearly this project that I had that was kind of sitting around, people do actually care about. So, I ended my GitHub streak before I moved from Amsterdam to Vancouver, just to give myself a little bit more time. And now I'm thinking, well, maybe I will, just sort of spend 2018, working on this performance book. So that's kind of where a lot of my free time has been going. And I'm up to, 5,000 words or something. And I haven't actually even gotten to any of the like Go specific optimization stuff. I'm just, just all my, other thoughts about, sort of performance and optimization and all that stuff that is really applicable to anything that you're building and want to make fast. So that's sort of the history of this perf book thing.
So your thoughts on performance, do they come from you exploring and experimenting, or they come from experience with previous production level application or a combination? And I just wanted to talk about this because I'm thinking, why would people be motivated to explore different ways of measuring performance? And or is it not even a worthwhile endeavor and they should maybe, for example, just read a book or look for what's out there? How should people approach that? And to answer that question, I guess I'm trying to assess how you approach going into this.
Well, so one of the things that I enjoy doing is obviously reading computer science research. And, most of that is, here's a better algorithm for doing, this thing. And, exactly how you measure better, varies. Sometimes they are faster, sometimes they are more accurate, sometimes they use less memory. But, a lot of, and the question is, how do you apply that? And how do you actually determine if this is a worthwhile paper, not just from a theoretical standpoint, but actually from like sort of practitioner standpoint? Do I actually want to implement this and put this into production? And so I think my interest in performance really comes from wanting to apply, computer science research in a way that makes sense. As to who should be, interested in performance, it really varies. It depends on, I'm going to say, sort of where you are in the stack. I think if you're building infrastructure, then, necessarily performance, I think, is a little bit more important for what you're doing, because there are more things that are sort of building on top of you. And, you kind of want to be as fast as possible because at the upper layers, sort of their speed will be, they cannot be faster than you are. And if you are very slow, then that kind of limits how fast they themselves can go. If, on the other hand, you are doing something that is, purely, customer facing, or, maybe a different kind of infrastructure, maybe you don't actually care about performance because your goal actually is shipping, right? Your goal is, I just need to get this out and I'm going to be customer focused. And you know what? They're not going to notice if it takes 500 milliseconds or if it takes 2 seconds, and my goal is to improve on, usability, or my goal is to improve on, like adding new features or making things better in that way. And then so performance really shouldn't be your primary thought.
So what percentage of Go developers do you think need to care about performance?
I mean, that's gonna depend. I mean, I see a lot of people. So for many people, the move to Go and sort of the move away from an interpreted language like Perl or Python, or even a very fast language like Node.js, the switch to Go is enough. You say, yeah, Go is twice as slow as C, but on the other hand, Perl and Python which are like, 30 times slower than C, all of a sudden by going to Go, you are now, 10 or 15 times faster. And that's simply by switching technologies. And so, for most things that people are doing, if you're in sort of what we would call a traditionally slow language, then moving to something like Go, probably is enough. And it's really the places where you're doing things where you need to be smarter about what you're doing, where you need to start thinking about performance. And I would say, again, at least, with my experience, at Booking.com, which is, like a huge company, lots of developers, massive code base. How many of them were focusing on performance? How many of them needed to be focusing on performance? You know what? It really kind of, varies. But I think that, the most important thing is what is the software that you're doing, and is it doing it, well enough? Is it doing it fast enough? Is it, using a reasonable amount of memory? And I think for most people, the answer is, yeah, it's doing fine. So it's really, a very small amount of people that actually need to, focus 100% on performance and really get those last, let's say like 10 or 20%, or 1 or 2%, to sort of, grind the cycles and really do the hardcore optimization. Everything else is, I mentioned this in the perf book. I say, you can, basic tips for writing not slow software. Choose a reasonable data structure, and that's basically like, don't be dumb. And then tips for writing fast software is, okay, here is actually what we're going to do, and this is how to minimize GC allocations. This is how to here's how to optimize GC performance. Here's how to really work around some of the issues with the runtime. But the first thing to write not slow software, just don't be dumb. If you're doing mostly sort of key-based lookups, use a map. Ta-da! Right? If you need stuff in order, use a slice. Ta-da! Just like choose the reasonable data structure for your data access patterns, and then that's kind of it. And then it's really after the program that you're trying to write, you determine that it isn't fast enough. I have an hourly report that takes an hour and a half to run. Okay, well, that's clearly not fast enough. I have, this box and I have to solve this problem, but all of a sudden I don't have enough RAM. If I do the obvious thing, then I don't have enough RAM to solve it. Okay, now we need to go in and shrink data sizes, compress data structures in memory, kind of do the extra that is required. But I think in almost all cases, don't optimize. But on the other hand, also don't be dumb. So
I'm waiting for that on Twitter. Don't be dumb. Quote.
Don't be dumb.
Don't optimize, but also don't be dumb.
It's going to be a meme. I see it already. Don't be dumb.
I can see using, but also don't be dumb a lot in so many different scenarios.
So once you've kind of decided that you need to optimize something, kind of what's your approach there to make sure that you're optimizing the right thing? Do you always profile first, or do you just kind of get like a gut instinct about where the problem lies?
Yeah, where do you even start?
So your gut instinct is always wrong.
Yeah, that's the truth.
Because that is the truth.
Not mine.
and the really good thing about sort of like profiling first is that you don't have to worry about other people who are like, oh, this is where your bottleneck is. You say, well, you know what? I'm dumb. I don't know where it is. I'm going to profile first. And so that the people who are too smart to profile, you can just ignore them. But so the whole point is you have to profile because your guesses are always wrong. Modern systems have, in general, so many interconnected pieces that if you say, well, I think this is the thing that's slow, maybe you're right, and that's great. Your profile will confirm your guess. Or maybe you're wrong, and then your profile will tell you where you actually need to speed things up. And then you won't have wasted time on optimizing something that isn't going to make a difference to the runtime.
I think sometimes your guess might be right as to where, but why might be wrong, right? like, oh, well, this particular function or section of code is slow, but you think it's actually the instructions when really it's the GC that it's causing or things like that.
But the point is that that a profile will tell you sort of where your bottlenecks are, and Amdahl's law tells you to focus on the bottlenecks, because that really limits how fast your program can go. If I have if my program is slow to start up, but that's only let's say 2% of my application. If I make that twice as fast, great. Well, now that's 1% of my application. So that's 1% of my total runtime, which maybe isn't that big a thing. If I have a hot loop, that profiling tells me, here's this hot inner loop, and this is taking 80% of your runtime. If you can make that only 10% faster, that will end up being a much more significant chunk of the total runtime of your program, and so that's where you should focus your efforts on. And I think that's the other advantage of profiling, is it says if you speed up this thing here, this will make sort of the biggest bang for the buck.
That's a very good point.
I forget where I heard it from, but somebody said something, like when you profile something, like focus on the biggest box first, and then just keep focusing every time you make a box smaller, focus on the next biggest one.
Yeah, because those are basically the bottlenecks, right? I mean, that's saying this is where your program is spending time. And so, either you want to take that thing that is slow and either make it faster by doing, like choosing a different algorithm, or, doing sort of, like program tuning, or, sort of, switching things around. Or at a larger level, you say, well, why is that box there at all? Maybe I can just, do something to not have this thing called as many times. All right. So if you're doing, so your program is doing either something that is not that slow a lot of times, or it's doing something that is slow. And so you either want to make that thing that is slow faster, or not do that thing that is slow as frequently. And those are kind of those are really the only two approaches that you can take to speeding something up.
Yeah, and Seago is a prime example of kind of like that expensive call thing, right? So if you can call into C less times, you can make Seago calls a lot more efficient.
And this is where you get into things like batching. So, I don't want to have to call into Seago every single time to do this. So I'm going to create an array of hundreds of 100 of these things, and then pass them all into Seago. So I only sort of cross that border once.
So in your book, are you going to list strategies like that too?
Um,
How
so
to handle, like how to fix performance, like which strategies to handle or even avoid performance issues?
yes. I mean, so the goal, like I said, the goal at the moment is to sort of take everything that I know about, sort of performance optimization, and sort of, like strategies, sort of in general strategies. And then I was going to go into sort of like Go specific things. So, like, how to use, pprof and the different profiles, and how to write benchmarks, and how to, like read pprof output to sort of know where it is you need to optimize. Stuff around like processor level fixes. So things around, cache lines and padding, and like concurrent access to like if you have a lot of Go routines, and sort of how to speed up accessing sort of the same data structures. Maybe like branch prediction. So really kind of like low level stuff that comes in. We're going to go into garbage collection. So minimizing allocations. Escape analysis, and and those kinds of things. Other things that show up when you're when you profile, so sort of runtime calls, all the the interface conversions back and forth, type assertions, defer, the bounce check elimination, so those kinds of things. I have stuff with unsafe. So like unsafe is unsafe, but it can also be fast. So stuff with Seago, some stuff with assembly, because obviously sometimes that is the way to speed things up, but not always. So I have cases where writing something in assembly has made like a 10x performance improvement. I've had a case where it made 0 performance improvement. The code that I wrote was essentially equivalent to what the Go compiler was generating. And I've had cases where my assembly implementation was slower because assembly routines aren't inlined. So, just sort of talking about all those things. So at the moment, I have sort of I have the larger sort of performance stuff and outlines for the sort of Go specific sections. But hey, it's only January, so I have lots of time.
The year is young.
Are you looking to complete it by the end of the year?
I have no idea. This is my hobby. We'll see what happens.
I'm kind of hoping you'll complete it before I have to teach my next Go performance class. Just FYI.
Which is what, next month?
Yeah, I don't know. Soon, probably.
Well, the first section is almost done. My sort of general performance thoughts, those are mostly done. It could use an editing pass, but it's the sort of Go specific things that sort of need more, I guess, writing about. And I suppose those to some extent are a little bit easier to, I guess, almost crowdsource, because it's not my personal opinion. All right. I mean, these things are sort of, it's like, well, how do you use unsafe? Well, I mean, there's kind of, one obvious way to use unsafe to, do these things. And so there's just kind of almost a tutorial section. So I think some of those, I think the later chapters are more tutorial sections, and those I think will be easier to write in a sense because you just have the things you want to write about and then you write about them. The first section about, when to optimize and basic strategies for optimization that are at the, sort of like bigger conceptual level, those, I think that's taken me a little bit more time because it turns out I've been doing programming a long time, and I've read a lot on software engineering and performance optimization, and I've done a lot of software engineering, a lot of performance optimization. So it turns out apparently I have a lot to say. I had no idea until I started writing it all down.
Are you enjoying it a lot?
I am. Actually, it's kind of good to get it all out of my brain and say, oh yeah, here's another interesting thing. And I think also because I've had a lot of these discussions, again, over time with people in the performance channel. So it's nice to be able to say, like look over here for my opinion on this.
Yeah, and we should mention that too, that on the Gopher Slack, there is a performance channel.
And that's mostly where you'll find me.
Here's the question too. So one of the things you talked about in the beginning too, like, is using data structures and algorithms that are, best served for your access patterns and stuff. So, that's awesome if you have like a huge vocabulary of them, right? So how would you recommend people get more familiar with more data structures and algorithms so that they can kind of have more to choose from? Or do you recommend with just kind of going with, your first pass being kind of how you imagine it, using just kind of standard things that are offered to you by the language, and then finding more efficient data structures later?
I think that really there are only a small handful of data structures that most people need to use on a day-to-day basis. And luckily, for the most part, they're built into Go already. So, I have a slice because I want sort of, order when append and I need random access, or I need to be able to, iterate things in order or whatever. Or I have a map because I have some sort of, key value lookup. And that really should cover almost everything that most devs want to do. And conveniently, that's why they're in the language. A lot of the more esoteric data structures have very specific use cases. And so you actually don't need to actually know how to write them, but it's helpful if you know that they exist. So I think that's, how did I learn them? Well, I mean, my background is like I have a computer science degree, and it was from a very basically theory heavy university. So I cracked open the books and I did all that work. Does everybody need to do that? No, probably not. Um, and so I think, how do you learn more about data structures? Pick one that you're interested in. But really, the number that most devs need to know, I think, is very small. It's nice to know, how a binary search tree works. It's nice to understand the guarantees that an AVL tree or a red-black tree give you versus a regular binary search tree. But if I was actually implementing those, I wouldn't use either an AVL tree or a red-black tree because they're both a huge pain to implement because they're really kind of annoying. And a treep is, gives you basically the same performance and is way easier to implement. So if I needed something that couldn't be solved by a slice or a map, and I needed the sort of, like log n, in order guarantees that a treep would give me, or sorry, that a tree structure would give me, then I would personally go with a treep because they're just simpler. But you kind of need to know the holes that the data structures that you have don't fill. And there's so many data structures out there. So pick some of the main ones. I'll learn those.
So, what are some that maybe pick 2 or 3 that you think if anybody had to wander off the beaten path might be interesting ones to know, or your favorites, just to kind of for people who don't have a list of data structures. What are some favorites or top ones you think people might go to?
Well, okay, so I think heaps are very useful because that kind of thing shows up frequently. Bloom filters, I think, are super
Oh
cool.
yeah.
Especially when you're doing performance work. They, just that ability to quickly say, do I have this thing or not? Do I need to do this extra amount of work or not? Bloom filters are really cool and, show up as a component of a lot of systems. For example, there's a cache eviction algorithm that I've implemented called TinyLFU. And, as part of this cache, it has a teeny Bloom filter that basically says, have I seen this before? And if I have seen it before, then I might see it again. So add it to my cache. But if I haven't seen it before, then don't put it into my cache yet, because it might be a one-off. And so, Bloom filters, by themselves are cool, but they're really cool as a component of something else. Yeah, I mean, I think, when I want to talk about data structures, because I've been doing this for so long, my views are heavily skewed toward the things that I find interesting. Count min sketches. There's a lot of probabilistic things that are cool that end up being simple but effective because they integrate randomness into them. Again, going back to treeps, they're very cool, really easy to implement. I don't know. Look at my GitHub.
I was just going to say, if you want to see some interesting stuff, just go to Damian's GitHub page because it's full of amazing implementations of technical papers. Every 2 minutes, he's announcing on Twitter that he found a new paper and then implemented it in Go. Here you go.
That's your slogan, implementing white papers so you don't have to.
It should be.
I love some of the stuff when they come around, when Raft came out. I love when people take these complex things and distill it down into a much simpler thing. Like the fact that what was the Raft paper, 11 pages, so much easier than some of the other distributed consensus algorithms that were around.
Paxos.
I tried to read the Paxos paper. I tried to read the Paxos paper. It's entertaining, but it's dense. And I think the fact that it's presented as this sort of basically the whole setup for the part-time parliament is, we've discovered, these historical things about this island in the Aegean Sea, about how this parliamentary system worked, and here it is. And then the last section is by the way, this also applies to computers. But the whole thing, I think, is really dense. You can try reading it. I did. I'm glad that Raft came out because I could understand. I mean, I understand how Paxos works, but not because I read it in the Paxos paper.
Yeah, and I think there's a bunch of Paxos implementations, and they're all implemented differently. It's everybody's interpretation of it was different. But
I thought I read somewhere that, and somebody who was very smart on Paxos said that he hadn't yet seen a Paxos implementation outside of Google that was correct. And that wouldn't surprise me.
I can believe that.
yeah,
Another thing that's interesting, especially with talking about Paxos, is I think the paper that Google released talking about Chubby, which is basically their implementation of Paxos, and I guess it's their implementation of Zookeeper, but whatever, Zookeeper was based off Chubby, and the Chubby implements Paxos, blah blah blah. Talking about how the algorithm that is in the Paxos paper is only one teeny component of what you actually need to build something that you can then, call a service. And there are so many weird other edge cases that were not, covered, in Paxos, and there are sort of, bits and pieces that you gather from these, like other papers to try to fill in the holes. But, like, is that sufficient? I don't know. I think the Chubby paper is really interesting paper to read from a software engineering point of view of really trying to put this theory into practice, and how even though these things like have proofs associated with them, how the the researchers and how the work that has gone into these papers is really this minuscule part of it, and trying to get everything together to build something that you can actually deploy. There's so much more extra work required.
yeah, and I mean, even if you look at Raft, right? Like Raft itself kind of explains how the consensus works, but you take like an implementation of that, like etcd or console or something like that, and there's so much more that goes into it, especially when you talk about having a service that can stand the test of time, that you need to be able to back up the data and compact logs and all these things, um, there's so much more work than just that. That's kind of the root of it, but like you said, there's so much more engineering and problems to solve around it. So moving on kind of from performance, another topic you are very into is fuzzing. So, for anybody who may not be familiar with what fuzzing is, do you want to kind of give a rundown on what fuzzing is, and then we can get into why you think everybody should be doing it?
So fuzzing is essentially randomized testing. So if you are, if you have some program that accepts input, from the user, maybe it's across the network, maybe it's a file. Fuzzing is basically, what are all the edge cases you forgot about? So there's fuzzing in general, and there's also the GoFuzz package that makes fuzzing easy for Go. But fuzzing in general is, I'm going to generate random inputs and throw them at your program and then see what happens. And the assumption is that your program should never crash. And if your program crashes, then I found a bug. GoFuzz is a tool for Go. It makes this very easy. You write a simple function called fuzz, and it will generate data and call this fuzz function. And GoFuzz works with what's called coverage-guided fuzzing. So it looks at the coverage that a particular input managed to get over your code base, and if that explored more cases, basically got good coverage and got into paths that a previous input hadn't, then it said, this is a more interesting input, so I'm going to keep this one and try and now sort of change around the bits of this input to see if I can get even more coverage. So coverage guided fuzzing makes it very easy to sort of narrow in on basically edge cases, things you hadn't thought about. So I love randomized testing. Testing is very good. Randomized testing is even better. And GoFuzz, I think, has essentially found crashers on almost everything I've thrown at it. So you find a repository and you say, well, hey, I'm gonna, like, did you manage to like check all your edge cases? And the answer is almost always no. And GoFuzz will find them for you generally very, very quickly.
Now, it would be even better if it could generate the fixes too.
So you should read up on the DARPA Grand Cyber Challenge.
Oh yeah.
That stuff was amazing. So these are fully I'm probably going to get this wrong, but basically, fully automated systems that had to both, I think, detect attacks against their code and patch them, and basically automatically generate patches, for these programs. And I think also there may have also been an attack component. I'm not sure, but seriously, Google the DARPA Grand Cyber Challenge, I think it was called, and watch. I know there's a YouTube video that I saw. This is just like a summary about this whole thing, and some of the work that was being done there was amazing.
That sounds like a good way to kill a day.
There was also a talk at Velocity, New York City this year, where there's some colleges and things that have come together, and they use like an AI ML component to kind of guess what the most normal or reasonable change would be to make to a piece of code to make it accurate. I have to remember the name of that talk, and if I do, I'll make sure it goes in the show notes. But along the same lines, where we can actually, feed these things in, and there's only a couple of, changes that a normal programmer might make to something, and it can kind of take a good guess at it. But yeah, eventually we won't need jobs anymore. Somebody's going to write the AI system that writes code for us, and they're going to be very rich. So yeah, fuzzing is actually good from not just a stability standpoint, but also from a security standpoint. Because generally, if you can make a program crash, you can take control of it. I mean, even at the least, you can cause a denial of service on it.
That's less of an issue with Go, obviously, because of the memory safety.
Right.
But definitely, if you're writing servers in like C or C++, then a crash generally means also exploitable. One of the other things you can do with GoFuzz is turn it not into so much, again, looking for crashes, but to compare two implementations. So I have a slow implementation and a fast implementation, and I will use coverage guided fuzzing to make sure that I explore all the corners of the slow implementation and the fast implementation, and then I will compare the output. And if the output isn't the same, then I will crash. And so then GoFuzz finds crashes, which means I have found a case where the fast implementation and the slow implementation generate different outputs.
Oh, that's cool.
Lots of use for fuzzing outside of just pure, sort of like, I guess what traditional vulnerabilities.
Here we go. I found it. It was called FTFY, Research Advances in Automatic Bug Repair, and some people out of Carnegie Mellon, and I will link to that. All right. So how are we doing on time?
Oh, it might be time to move into news.
I think it is. So first off, 1.9.3 was released a couple days ago. So update now. Submit bug reports because we know none of you tested it while it was in beta.
There isn't really much in this one. I looked at the GitHub issues and they were pretty light. I mean, there's nothing huge.
Yeah, it was some minor bug fixes and stuff. There was no major security stuff that I recall.
The biggest one I remember seeing was a database connection leak, I think. And it had something to do with transactions, but overall, one of the more minor of the point releases, which is good. We like tiny little bug fixes.
1.10 will be out soon. I think so. I think RC1 is out, or will be out probably by the time you hear this, not live. And I think they were targeting like mid-February for 1.10. So again, that's not very far away.
Oh yeah.
Yeah, they just keep coming. It's amazing how fast these 6-month release cycles go. I love it.
It takes them about 6 months.
Yeah, and speaking of performance, that's one of the things that I've always loved about Go, especially like coming from pre-1. Like the amount of performance change is crazy, and you didn't have to do anything. You just
Just download a new compiler and smile.
and then recompile, and you're like, "Woo, it's faster."
Yeah. Yeehaw. That is awesome, and that kind of underscores what Damien was talking about earlier. When if you came from a language that was already not so awesomely fast, Go was huge. When I moved from Ruby, it was a big speed difference, and then I moved to Go 1.1, and then 1.4, and then 1.6, and it just keeps getting faster. It's the gift that keeps on giving. All right, I found a project for news called Skydive. It's at github.com/skydive-project/skydive. And it bills itself as an open source real-time network topology and protocol analyzer. And I got to be honest, I really don't care about that. But the graph, the interactive little thing on their GitHub page looks really cool, and you can just dive in and look at all the different nodes on your network and the protocols that are traveling between them. So makes you feel kind of CSI-ish, and you should probably download that just to impress your friends.
Oh, that's awesome. I really want to use this from a security standpoint, like, because sometimes trying to map out what machines are talking to what other machines to try to find new attack surfaces, like, that's wicked cool.
I'm surprised you hadn't seen this one yet. This is right up your alley.
Yeah, I have not seen this. This is really cool. So I've got one too. I think we mentioned it on the show before, but there's a project called Metaparticle, which is kind of this exploration of building an abstraction over Kubernetes and Docker and all these things, and exposing them to your programming language and framework of choice where they're kind of embedded in the language. They now have Go support, so you can now write a Go program that compiles itself, or compiles, then when you run it, it containerizes itself and deploys it. And it can do crazy stuff like sharding for you automatically. You say, I want to be spread out across 2 shards. Here's my shard key. And it kind of does the right thing and creates all the Kubernetes components to do that. Just super cool.
Yeah, Metaparticle as a whole is just an amazing idea. And then adding to that the idea that you're going to, when you go run this application, it's going to deploy itself to a cluster in a way that you've programmatically declared. That is just really cool.
Then, as always, the Just for Funk stuff. There was a recent one where Francesc does a awesome job talking through channels and nil channels and why they even exist.
All of Frances's videos are just so amazing.
I know. I feel like I've missed a few of them. I need to binge watch them.
That might have something to do with him being so amazing, but I'm not sure.
Possibly. I think that's a really good point.
There's a slight chance, but no, Francesc is awesome. Anything else? Move on to Free Software Friday.
Yes.
And Damian, you've listened to the show, so you kind of know what the Free Software Friday thing is, right?
Sure. Sure. Yes, of course I do. I want to give a shout out to I guess Andy Bonds on Twitter, GitHub, Andrew from the Go team, who is slowly working through all the GoFuzz bugs to get GoFuzz integrated into the main Go tooling. I think that will be amazing. So even though it's kind of his job, I think still a cool shout out for that, because I think that'll make a really big difference just to getting sort of better, like really good testing, like just in with the Go tool and you don't have to do anything else.
Yeah, that would be amazing. Do you know roughly what milestone they're targeting for that?
I have no idea.
How about you, Carlicia?
I don't have anything today.
Does that mean I can do 2?
Yeah.
You can do
That's exactly
3,
what it means.
because
Yes.
I've spent this whole week working on slides, so I haven't used a tool for one to kind of pop in my head right now.
Awesome. So I have to go with a fun one that I constantly use and never remember that I use, which is the Pretty package from Keith Rarick. Every time I want to debug, we don't debug in my house, we just format print line. But KR Pretty is a package that dumps pretty much any object you can think of to the screen in a pretty format. So instead of format.println, kr/pretty.println, and you get a nice JSON human readable output of all of those objects. My only complaint is that if you've got a really big type, it parses that whole thing and goes all the way down. So you might end up with hundreds of lines of output for one type. But that's what you asked for because you're debugging. So it's awesome, and I use it pretty much all the time. So that's one. That one will be mine. And then for Eric, I would like to thank Richard Musial, Musiol, who's Neelance on GitHub. He is working really hard right now on the WebAssembly compiler for Go. And I stumbled across his Go fork that has WASM support last night and just sat in awe looking at how close it is to being done. And I can't tell you how excited I am about WebAssembly support for Go. That's going to be amazing.
Yeah, that I actually saw that in, I think, one of the Golang weekly newsletters, and I meant to read that because I think all the WebAssembly stuff is just killer. All right, so I think that's it. We're like perfectly timed this week.
Did we hit it right on the head?
Yeah.
That's awesome.
So with that, I want to thank everybody for being on the show. A huge thank you to Damian for coming on. All of us will keep an eye out on your perf book, and we'll be cheering behind the scenes, and I'm sure plenty of people will be willing to review it for you.
Yeah, hurry up and finish it so I can steal all your content. That'd be awesome. Thanks. I mean, borrow. Did I say steal?
Damn. I think the license allows you to steal.
Oh, perfect. Thank goodness.
CC by SA. At least that's what it is for the moment.
Damian wrote this.
So thank you to all of our listeners. You can find us at gotime.fm. We are at gotimefm on Twitter. If you have suggestions for guests or topics, or you want to come on the show, you can file an issue on github.com/gotimefm/ping. And with that, goodbye, everybody. We'll see you next week.
Bye.
Bye.
All right, that's it for this episode of Go Time. Tune in live on Thursdays at 3 p.m. U.S. Eastern at changelog.com/live. Join the community and Slack with us in real time during the shows. Head to changelog.com/community. Follow us on Twitter. We're at GoTimeFM. Special thanks to Fastly, our bandwidth partner. Head to fastly.com to learn more. Also, Linode. We host everything we do on Linode servers. Head to linode.com/changelog. GoTime is edited by Jonathan Youngblood, and the theme music for GoTime is produced by the mysterious Breakmaster Cylinder. We'll see you again next week. Thanks for listening.